Okay, namaste. Today our discussion is about the Newtonian flow, right? We already know about the Newtonian flow and we have studied the Newtonian flow sometimes back. But what is the necessity of implementing that Newtonian flow here, Newtonian theory, right? So, so far in hypersonic flow, we had a discussion on various phenomena. And then, while deriving the Shockwave relation, we always focus on calculating the coefficient of pressure, right? So, the coefficient of pressure we try to calculate because our ultimate idea is to calculate the forces acting on the hypersonic vehicle, right? So, in this, we have various approximate methods, right? So let us start with an approximate method which is given by Newton quite long back, 350 years back or so, but still we can use the approximation given by Newton, right? So I acknowledge the book John D. Anderson's Hypersonic and High Temperature Gas Dynamics, right? Now, we already know that the hypersonic flow is inherently nonlinear, right? Because we have a discussion that the hypersonic flow is affected by the various phenomena, right? It is not only the one particular Mach number. We can say that it is hypersonic flow where m infinity is equal to something like 5 or 6, but we had a discussion that this is because of the thin shock layer, entropy layer, viscous interaction, high temperature, low density, high density ratio. Like that, we had a physical aspect. Right? Hence, we can say that the hypersonic flow is non-linear, right? But we have a point, right? When even though we say the hypersonic flow is based on various phenomena, but when there is a supersonic flow theory, which we can adapt to the hypersonic flow, that will be much better. Say, for example, you know, we can go with, okay, so we will have a point. So, with the consideration, the basic inviscid compressible flow theory can be applied, right? So, but that shows that it is a very linear relationship, right? The coefficient of pressure, which is in terms of theta, right? So, theta is a deflection angle, right? Theta is a deflection angle, right? And m infinity is the free stream velocity. But here the body is considered to be thin at a small angle of attack, right? So we can express the Cp for the supersonic flow, correct? But still there is a problem. We cannot directly use this in the hypersonic flow because the flow phenomenon is different, right? So we go to a new method called local surface inclination method. Okay. So the method called the local surface inclination method, we will see how we can apply the Newtonian law, right? So it is called the local surface inclination method. This is one of the approximate method to calculate the coefficient of pressure when it is subjected to a high velocity or high Mach. So, in the propositions 34 and 35 of his Principia, Newton published in 1687, he modeled the fluid flow. So, he modeled the fluid flow in such a way that a stream of particles in a rectilinear motion, right? It is almost like a pellets from a shotgun. So when it is striking, right, So it would lose all its momentum normal to the surface and move tangentially to the surface without any loss of tangential momentum. So here we can model that, right? So this is a V infinity. We assume that a pellet which hits here, right? So this stream of particle in a rectilinear motion, this is almost like a pellet, right? It can be like a pellet. So which is striking on the surface would lose all its momentum normal to it, but it moves in a parallel to the flat plate, right? So this inclination, this theta can be considered as an inclination angle, right? And v infinity is a free stream velocity. So we can solve this in x and y, and then we can proceed further, right? So um, let us say, okay, so we have this, we need to calculate the change in normal velocity, right? So let us say change in normal velocity. So what is change in normal velocity? We can write that it is v infinity sine theta, right? We can solve it and we can say that the change in normal velocity can be v infinity sine theta. Okay. Now let us go again to the next one. We want to calculate, actually we want to calculate the force acting. You know very well that the force acting is, say if we know the force, if we know the pressure, we can calculate the force because pressure is equal to force by area, right? So if we calculate pressure, force, by this calculation, we can calculate the pressure and we can calculate the Cp also. So let us go back. So we know that this is v infinity sine theta, the change in normal velocity, and let us write here itself and say um, say mass, right? Mass flux. So mass flux incident on the surface. On the surface, let us say the surface is area A. So we can write the mass flux as rho infinity, v infinity, A, right, and sine theta. It's rho A V, right? So here we consider rho infinity, v infinity, and A sine theta, right? Now we have a mass flux. Now let us calculate the time rate of change of momentum, right? The time rate of change of momentum of the mass flux. Let us say the time rate of change of momentum, time rate of change of momentum of the mass flux, right? So we already have a time rate of change of momentum of a mass flux. We have like rho infinity, v infinity, a sine theta, which can be multiplied by again v infinity sine theta. Right? So rho infinity, v infinity, right? We know that we can calculate, you know, you can check the dimensionally balancing or not. and so change in momentum of a force, change in momentum of a force is necessarily, rate of change of momentum. We can say, according to the Newton's second law, the rate of change of momentum is directly proportional to the force. Now we can write this equation as rho infinity v infinity square a and sine square theta. Okay. Now, according to the Newton's second law, time rate of change of momentum is directly proportional to the force, right? Let us say F is equal to the force exerted, right? I can say that this is rho infinity v infinity square a sine theta. So here F is the force exerted, right? Then according to Newton's second law, we can write the F is equal to rho infinity v infinity square a sine theta, right? So again, um, let us say here we can write something like F by A. F by A, what is F by A? This is necessarily pressure, right? Rho infinity v infinity square and sine square theta, right? Here it will be sine square theta. So here the point we need to notice, the Newton assumed the stream of particles to be in a rectilinear motion, right? So that is, he assumed that the individual particles do not interact with each other and have no random motion, right? That is the point. But due to the lack of random motion, F is a force associated only in the directed linear motion, right? So, in the modern science, in the modern fluid mechanics, we say that the static pressure of any gas or a liquid is due to the pure random motion, right? Do you remember the collision and this random motion of these particular molecules in the air, which in turn produces the static pressure, right? So, which is not included in Newtonian theory for some times back, right? Maybe 350 years back or so. Now, um, so we can now calculate. We know already the F by A, right? Okay, let us say F by A is equal to rho infinity v infinity square and sine square theta. So F by A can be equated dimensionally to the pressure, right? Right. So in our case, we what we do is like we normally consider this as not simply pressure, but it will be a pressure difference, right? So okay. So let us say F by A is equal to P minus P infinity. So this P minus P infinity is the pressure difference above the free stream static pressure. Right. So the free stream static pressure. Now we can arrive to a simple solution, right? Say, for example, have some approximation and say we can write P minus P infinity, that is equal to rho infinity V infinity square sine square theta. So I can write something like P minus P infinity P minus P infinity by rho infinity d infinity square, that is equal to sine square theta. Now let us say I divide this, like, say we can write in terms of, like, here I write like off, then necessarily I can multiply 2 here. And can you imagine what this is? This is actually the coefficient of pressure, coefficient of pressure. So here we can write finally the Cp is equal to 2 sine square theta. Of course, this also has some limitation, right? This Cp is equal to 2 sine square theta is a famous Newtonian sine square law for pressure coefficient. Right? So this is sine square law of pressure coefficient. Right? So Cp is equal to 2 sine square theta is what the final point is. Right? So let us revisit it once again. We know that basically in the principle, Newton expressed he modeled the fluid flow of a stream of fluid particles in a rectilinear motion. It is much like a stream of pellets from a shotgun blast, which strikes the surface and lose all its momentum, normal to the surface, but would move tangentially to the surface, right? Here it moves tangentially to the surface, right? So here we can say that the change in normal velocity can be v infinity sine theta. Again, mass flux, we can express mass flux incident on the surface A. Let us say this is a surface A, and we can write rho infinity v infinity into A sine theta, right? Then the time rate of change of momentum of the mass flux we have calculated, right? So m into v infinity, so rho infinity m dot, right? Sorry. So rho infinity v infinity a sine theta multiplied by v infinity sine theta, that becomes rho infinity v infinity square a sine square theta. And we know that according to the Newton's second law of motion, we can say that the force exerted on a surface uh, can be equated to time rate of change of momentum of flux, right, mass flux. So F is equal to rho infinity V infinity square A sin square theta, and let us bring this A down. So it will become F by A is equal to rho infinity V infinity square sin square theta. But we have a point here that the random motion of the fluid particle is not considered in the derivation of the Newtonian theory here. So F by A can be the rho infinity V infinity square sin square theta, and P is equal to the pressure difference, which is above the free stream static pressure. Right? So we can write F by A is equal to P minus P infinity, and P minus P infinity equal to rho infinity square V infinity square sin square theta. Right? So this becomes like, let us multiply 2 on both sides, and then we can get P minus P infinity by half rho V square is equal to 2 sin square theta. We know this is Cp, right? So Cp is equal to coefficient of pressure, that is equal to 2 sin square theta, and this is famously known as Newton's sine square law of pressure coefficient. Okay, so I stop at this point for the Newtonian flow or Newtonian law. So let us discuss the modified form of Newtonian flow in the next class. Right? So ultimately, our aim is to calculate the coefficient of pressure that we have calculated. Right? So I stop at this point. Right? Thank you very much.